Assalamu alaikum dear students, welcome back to my channel. In today's lecture we are going to prove the basic comparison theorem for investigating the convergence of infinite series. Okay, what does it say? It says that if you have any two series which are of positive terms infinite series, okay, and these two series there is a relation between their terms. This is the relation, an is less than I times bn, where I is any positive real number and this n is greater than or equal to k, where k is any positive integer. So if how will they depend on each other? If the series summation bn is convergent, then the series summation an will be convergent too. Okay, and the second part is actually just a contrapositive statement of this one. It says that if this series, the summation an series, is divergent, then summation bn series will be divergent too. Okay, let's start our proof, but before that I am showing you the pictures of two results that we are going to use in today's proof. Alright students, I assume that you people have gone through those two pictures of the results that we are going to use in our proof. So let's start our proof. We are starting our proof with the assumption that the series summation bn is convergent. If it is a convergent series, then it must satisfy the general principle for convergence of infinite series. So we can say that for any epsilon greater than 0, there will exist a positive integer n naught such that summation bi, where I runs from n plus 1 to m, will be less than epsilon over I for all m n greater than n naught. I have chosen this number very carefully because this is going to help me a lot in proving what I want to prove. Okay. Anyhow, we want to see whether the series summation an also satisfies the general principle for convergence of series. Because if it satisfies 2, then it will be convergent as well, just like this series. So let's see whether it will satisfy the condition of general principle of convergence of series. We are going to take the same sum ai, where I runs from n plus 1 to m, where n and m are same. They are greater than n naught in this case as well. Let's see how will it behave. Now, by using the relation an is less than I times bn, can I write this as I times summation bi, where I runs from n plus 1 to m. Okay, and then I'm going to replace this expression as follows: I times, we know that this expression was less than epsilon over I, so we can write here epsilon over I. Now cancelling these two, we will finally have summation ai, where I runs from n plus 1 to m, as less than some positive real number for all m n greater than n naught. What does that mean? It means the series summation an has also satisfied the general principle for convergence of infinite series. It is satisfying all the conditions of that principle. So from here we can say that the series summation an is also convergent, right? Alright students, let's go to the second part of the theorem, which says that the series summation an divergent implies that the series summation bn will be divergent too. Okay, so let's assume that the series summation an is a divergent series. Okay, now if you are saying that this series is divergent, then I claim that its sequence of partial sums will be unbounded. How can I say this for sure? Because the series we are considering is of positive terms. Okay, so this sequence of partial sums will be a monotonically increasing sequence. So we know from real analysis course that if you have a sequence which is monotonic sequence, no matter whether it is monotonically increasing or monotonically decreasing, if it is bounded as well, then it will be convergent. Okay, so the only thing that can prevent this sequence to be a convergent one is if this sequence is unbounded. Okay, so that is why we are saying that this series is divergent, then this sequence of partial sums will be unbounded. That is the only possibility. Okay, now if you are saying that the sequence of partial sums for this series is unbounded, that means that the difference of any two terms of this sequence will be increasing as we move on in this sequence. Okay, so I can write it as summation of ai's, where I runs from n plus 1 to m, will be greater than I times epsilon. I can choose any positive real number, so I have chosen this. This is my choice, you can take any, but this I think is going to help us in proving what we want to prove here. Okay, so using this expression we will prove that the series summation bn is divergent too. Okay, so let's see what will happen to this series in this case. Let's take the expression summation bi, where I runs from n plus 1 to m. Now using this relation, we can write that this expression will be greater than 1 over I times summation of ai's, where I runs from n plus 1 to m. And as we know that this expression is greater than I times epsilon, so I can write it over here as 1 over I times epsilon. Okay, and then cancelling these two, we will finally have summation of bi's as I runs from n plus 1 to m, that is greater than epsilon, where epsilon, what is epsilon? It is any positive real number. So no matter how small or how large you choose epsilon to be, the difference of consecutive terms or any two terms of the sequence of partial sums will be increasing, will be greater than your chosen positive real number. Okay, so this is actually violating the condition that a positive term series converges if and only if the sequence of partial sums is a bounded one. But here the difference of any two terms of sequence of partial sums is actually greater than any chosen positive real number, which means that this sequence of partial sums for the series summation bn is unbounded. That is why we can finally conclude that the series summation bn will be divergent as well. Okay, I hope so this will be clear. Thank you so much for watching the complete video. Please like and share this video, subscribe my channel and hit the bell icon so that you don't miss any update in the future. Thank you so much.